Solving exponential equations. So if you have a common base, right, remember, power is made up of a base and an exponent. If the base is common, then you can solve algebraically, right? Like 7 to the x minus 1 is 7 to the 3x plus 2, so what can we say? What's got to be the same? So the bases are the same, which means the exponents must be equal to each other, right? If this statement is true and the bases are the same, then we can say, well, that means that x minus 1 must be the same as 3x plus 2. Which now allows us to solve that, right? Algebraically. Which means we move this over here, we'll get negative 3 is equal to 2x, so x is equal to negative 3 halves. Okay, and you can verify that. You can go 7 to the negative 3 halves minus 1, and you go 7 times 3 to the negative 3 halves plus 2. You get the same answer. Okay, but this one, the bases aren't the same. We got a 3, we got an 81, so whatever could we do? Okay, can't multiply both sides, but what's 81? 9 squared. 9 squared, but what else is 81? 3 to the power of 4, right? So if we can write 81 with a base of 3, so we go 3 to the x is equal to 81, except we're going to write that as 3 to the power of 4 to the x plus 2. Then on the next line, we're just going to use our exponent laws, right? So 3 to the x is equal to 3. What does this become?
3 to the 4x.
Yeah, 4x plus 8, right? It's 4 times x plus 2. Okay, now what can we say?
X is equal to 4x.
Yeah, x. If the bases are the same, and the equation, the equal sign says the left side and the right side are the same. If the bases are the same, then that means that x must be equal to 4x plus 8. So negative 3x is 8, and x is negative 8/3. Okay, and again, that's checkable by just putting that in. You go 3 to the negative 8/3, and you go 81 to the negative 8/3 plus 2. Excuse me. It equals on both of those. They should come out the same. Okay, so again, the idea is now let's look for a common base. What's a common base between 1/5 and 125? 5. Both powers of 5. What's 1/5 as a power of 5? 5 to the negative 1. Okay. So what we do is we want to rewrite the base as a power of whatever we decided is common. And 125 as a power of 5? 3. So 5 cubed to the power of 4x. Okay, at this point we then go to power to a power, right? Which means we multiply the exponents. So this becomes 5 to the negative x plus 1 is equal to 5 to the 12x. So now that the bases are the same, they're both 5s, what do we do with the exponents? You equate them, right? You say, if this is true, if 5 to this power is equal to 5 to that power, then this and that, these expressions, negative x plus 1 must equal 12x, which means 1 is equal to 13x, and x will be 1 over 13. Okay? Now we can verify it here. I'll pull out the calculator. Whoops. What's going over there? Let's just try this and see, right? So, all right, let's close the calculator and reopen the calculator. So I want to do 1/5, bracket 1 divided by 5, bracket, to the power of 1/13. How do you get a fraction of this thing? What was that? No, but there was somewhere where you could enter a fraction. Oh, here we go. 1. Okay, so 1/13. And then what do I got to do? 13th. Go over here. Minus 1. Okay. Yeah, there's another way. If you have a less able calculator, if you don't have the latest firmware, but I could do this. So we got that number, and then I've got 125 to the power of 4 times. And then I want that again, 1/13, so 1/13. So what should happen when I hit enter? Okay. Get the same number, right? So let's make it really is 1/13, right? X really is 1/13. Now that's something on a test, you don't do that until you're done, right? You do that at the end maybe. Okay, a little more complicated expression. What's the common base for 9, 81, and 27? They're all powers of 3. If it was just 9 and 81, we could go with powers of 9. Okay, but it's not. So what's 9 as a power of 3? 3 squared. So we got 3 squared to the 2x minus 3. What's 81 as a power of 3? 3 to the 4. Okay, and we put them in parentheses, right? It's 3 squared, right? We're saying this is the 9, this is the 81, to the 2x minus 4. Is equal to 27 is 3 cubed to the 4x. What we're going to do is work this until we end up with the left side saying 3 to some power is equal to the right side saying 3 to the 12x. So that's what the right side is going to be. So this becomes 3 power to a power, so 4x minus 6 over 3, 8x minus 16 is equal to 3, 12x. Okay, what do we do with 4x minus 6 and 8x minus 16? You've got to subtract, right? Okay, so how much detail do I want to show here? Detail, not much. Okay, so 4x minus 8x will be negative 4x. Negative 6 minus negative 16 is plus 10. And that's equal to 3 to the 12x. We're running out of room. Stay on the page. So now what do we say? Yeah, negative 4x plus 10. So the bases are the same. So 10 is 16x, and x is 10 over 16, or 5/8. Okay, again, you could check this in the original. I'm not going to. It would take too long, right? But I mean, if you felt like it, you could do that. You could also solve that graphically. You could graph this as your left side, you know, y1, y2, look for the x coordinate of the point of intersection. That's something you got to state when you're doing a graphical determinant, right? The x coordinate of the point of intersection. Okay, 6, 36, and 2, 16. Base 6, okay? They're all power set. Okay, give this a shot. Give it a try. You can do it. I will pause this. Okay, so we express with powers of 6, so the top just becomes 6 to the 6x minus 2. Bottom is 6 squared. To evaluate that, you're going to go 6x minus 2 minus 2, because you're going to subtract the power in the denominator. So you get 6x minus 4. Right side, 6 cubed, which is 216 to the 4x, gives you 6 to the 12x. Once we're at this line here, we simply equate the exponents and solve for x. 2, 8, and 128. Common base is 2. Okay, 2 to the x over 2. What's root 8? So 8 is 2 cubed. What's a square root as an exponent? What exponent gives you square root? 1/2. Is equal to, finger, 2, 4, 8, 16, 32, 64, 128. 2 to the 7th. Let's use fingers for powers of 2. It's good up to 1,024. Then you got to use toes. But if I can see mine, it's fine. Okay, so we've got 2 to the x over 2 times 2 to the 3/2 is equal to 2 to the 28x. So what do we do with x over 2 and 3 over 2? You add them, right? What do you get? X plus 3 over 2, right? They have a common denominator of 2. And that's equal to 2 to the 28x. Okay, so we're now down to the point where we have 2 to something is equal to 2 to something else. So now we equate something and something else. So we equate x plus 3 over 2 with 28x, or over 1 if you like, cross multiply. X plus 3 is 56x. So 3 would be 55x. And x would be 3 over 55. You know, and you get a nice exact value. You're not going to get, you get some decimal which you would have to convert to a fraction if you were doing this on your calculator, right? But here we get exact values. Remember what exact values are, right? Fractions, radical, reduced radicals, etc., not decimals. This cannot be expressed as an exact value, right? You have to go negative 0.6 repeating, okay, which is ugly, right? A repeating decimal, whereas negative 2/3 is a nice exact value. All right, 3, what do we do here?
I can multiply the 3 and the 4 and have just one big thing on the left. And
Like 12?
Yeah.
Who thinks you could do that? Sorry, you got no backup. Divide both sides by 3. Why don't you get rid of the 3? When you do that, remember, math is like chess. Look ahead. If I divide by 3, I'll get 32. Oh wait, 32 is the power of 2, and so is 4. All right, good. So once we divide both sides by 3, we're laughing, right? So that's the first step. You're going to want to do that for the rest of this unit. If you see 3 times and then some base, like get rid of the 3. Okay. You can still do things without doing that, but not easily. In this one, you can't. You can't solve this if you don't divide both sides by 3. Okay. Now, it's not too bad, right? So 4 is 2 squared. Put it in brackets again, just so you remember. What's 32? 2 to the 5th. Okay. So you should know your powers of 2, right? Or just count on your fingers. 2, 4, 8, 16, 32, 64, 128, 56, 5, 12, 10, 24. Power to a power. Equate the exponents. There's actually a mathematical thing we can do that allows us to do that. We just don't know it yet. So we're just saying, okay, you can equate the exponent. So 4x is 15, and x is 15 over 4, right, as an exact value. Okay, and again, exact value would be a reduced fraction, and that's reduced to 0. Okay. You're going to see these. What could we do with this? You could. It's not going to help you. Here, let me write this. So let's take 4 to the 2x and write that as 4 to the power of x squared minus 6 times 4 to the power of x plus 8 is equal to 0. So what does that remind you of? Yeah, factoring. It's a quadratic, right? It's something squared minus 6 times the same something plus 8 is equal to 0. Okay, so for that something, let's just say, well, let a equal 4 to the power of x. Right? Now, so if I write a squared minus 6a plus 8 is equal to 0, then you go, okay, obviously you solve that by factoring, right? So you got this 4 to the 2x, you got the 4 to the x, you get suspicious and you say, oh, right, it looks a lot like a quadratic. And when you write it as 4 to the x squared, now it really looks like a quadratic, right? Because something is being squared. And then you're subtracting 6 times that same thing. Okay, so how does this factor? A minus 4, a minus 2. Okay, so a squared minus 2 minus 4 is minus 6 plus 8. Okay, so that all works. So a is equal to 4, or a is equal to 2, but there's no a. So what do? You go back to 4 to the x, right? So if a is equal to 4, that means that 4 to the x is equal to 4, so what's x? 1, right? Because there's a 1 there. And it means what? It means that 4 to the x is equal to 2. So what's x? Okay, it's 1/2, right? But you could go 2 squared to the x is equal to 2. You could throw 1 in there if you like. So you go 2 to the 2x is equal to 2 to the 1. 2x is 1, x is 1/2. So if x is 1 or x is 1/2, this is going to solve, right? It's going to be a true statement. Right? So we're going to see a lot of that. It's just like sine squared x. It's the same deal, right? You've got a quadratic in sine. You've got sine squared x minus 2 sine x plus 7 is equal to 0. Okay, factor. Solve. Explain how you could solve 1c graphically. 1c. 1c. 1/5 to the x minus 1. Okay, so explain would be like saying graphically determine. We're not actually going to solve, but we're going to say here's what I would do, right? So graphical determination, requires the following. All right, so you're going to say, I just got to go to a sheet where I can actually see it. Graph. y1 is equal to 1/5 to the x minus 1. Oops, y1. y2 is equal to 125 to the 4x. Pick an appropriate window. So an x window. Now we already know the solution for 1c is 1/13, right? So we don't have to go that big. We'd say go from -1 to 1 by 0.5. I mean, you can add your window after you values. So y values, again, you kind of arbitrarily choose those. After you graph it and sort of see where the intersection is, you can go in a little bit tighter on it, just making sure you're seeing some stuff. But you just need to state a window which is reasonable, right? That I can see the solution in, or in which you can see the solution. And then what? Then the important point, right? Which is find the x value. Find the x value of the intersection point, because that's where the solutions are, right? Find the x value of the intersection point. Okay, so if we're going to graph this, let's give it a shot. Go to y equals. So I'm going to do 1/5. I could do my fancy fraction stuff, right? 1/5. If you don't have the fancy fractions, just go bracket 1 divided by 5 bracket. So 1/5, then I got to arrow over. Okay, to the power of, what is it, x minus 1? X minus 1. Okay, and again, if you don't have this version of firmware on your calculator, go bracket 1 divided by 5 bracket to the power of bracket x minus 1 bracket, just to ensure. And we've got 125 to the power of 4x. Okay, so just take graph. Here's the standard window, right? Now we should know what 1/5 to the power of x looks like, right? It's decay. And we should know 125 to the 4x. It's going to be getting pretty big pretty fast. So we can see, well, it's there, right? So I don't need to look too far. Okay, so we can close in. So we're saying, well, let's go from -1 to 1.
Can't you do the box? Maybe easier.
Yeah, you could, but we're asking you to state a window, right? So -1 to 1 by 0.5. And then -2, just so we can see the graph. We know that the intersection was visible on the window. Okay, so we're just graphing and gotta wait. So that's 1/5. That's the decay function, right? It's coming down. Then we've got the growth, which we know is going to go through 1. But it climbs really fast, right? Because when this is 1, it's going to be 125. Okay, second calc. Find the x coordinate of the point of intersection. So I just move there and go 1, 2, 3. And we get 0.0769. 2, 3. So x equals 0.76. Okay, but what we want to do then is just, so the x is here, so just go x, math, enter, enter, which says change the x into a fraction. Okay, so the x is stored for you, right? When you do the second calc intersect, the x is stored in x. So if I just hit x and say enter, that's what it comes out. And then I say math, enter, enter, convert the answer to a fraction, we get 1 over 13. Okay, so x is equal to 1 over 13, right? So you just do a 2 frac. Okay, convert the x to a fraction. Okay, so that's graphical solution. You need the following, right? What am I graphing? y1, y2, here's my window. This is what I'm doing with the graph. I'm finding the x value of the intersection point, right? Find the x coordinate of the point of intersection. Something along those lines.
Just to go back, it's 0.07.
Okay, fix that up. Number 3. Transformation. The graph of y equals 2 to the x is transformed to the graph of y equals negative 2 bracket, or sorry, negative 9 bracket 2 to the x minus 5 plus 36. Describe transformations, correct order. So number 1, what's up? Vertical stretch by a factor of, stretch by a factor of 9 about, the x-axis. Okay. Just to add that back in, I know we haven't done a lot of description of transformation, so it doesn't hurt to. Followed by what? Reflection in the x-axis. Followed by horizontal translation, right 5. So horizontal translation. You just got to say which way how much or how much which way, so 5 units right. And lastly, vertical translation. Which way? Up 36 units. So the translations need which type, is it horizontal or vertical? How much which way, or which way how much? Okay, so like vertical would be up or down 36, or you could say 36 units up, 36 units down, etc. State the following for the graph. So you don't need to show any justification for this, right? You're just writing down an answer. What's the domain? Yeah, so set of all x such that x belongs to the reals, right? That's every exponential function has that. We cannot change it, right? Nothing that would change that. What's the range? Y such that y. Sorry? Less than or equal to 36, yeah? Oh, sorry, just strictly less than 36, right? Sorry. Which leads to the equation of the asymptote being y equals 36. Okay? So if you think about it, it's like, okay, well, we started with something like this, then we stretched it, then we reflected it, and then we moved it up and over, right? So that the asymptote line at 0 is now up at 36, okay, because of the reflection. Determine the x and the y-intercept. Okay, y-intercept, what do? Okay, so we set x to 0, set x equal to 0. So y is equal to negative 9 to 0 minus 5 plus 36. Negative 9 times 2 to the negative 5th plus 36. Negative 9 over 32 plus 36. And if we want that as an exact value, so what do I got? Negative 9 divided, oh wait, let's do my fancy fraction thing. So it's negative 9 divided, oops, fancy fraction. 32 plus 36, math, enter, change it to a fraction. 1143/32. Okay, you work on the x-intercept. Football game now they do. Set y equal to 0. That game being the city championships tomorrow, 4 o'clock in Canna Field at Shoaldice, junior football against St. Francis. So, you know, come on out. It's supposed to be reasonably nice weather. Cheer on the boys. And girls. There's 2 girls on the team as well.
Really?
Yes, there are.
I thought there was 3.
Okay, there's at least 2 girls on the team. I can only say I knew of one, and then somebody said, oh, there's another. So, okay.
What position are
One's a DB. So negative 36. Yeah, I'm not sure of the others.
that? Is.
Okay, what do we do? So we've done that, now what? Divide by -9, right? So you're going to see this a lot coming up in the next number of days. We got this stuff, like get rid of it. Simplify stuff before you start doing things. See, because now this is easy to solve, right? Because 4 is 2 squared. And that's 2 to the x minus 5. So 2 is equal to x minus 5. So x is 3, right? Yeah, it's actually 7. I knew that. Just waiting for somebody to say, wait a second. The common thing, right? Because a lot of times you look at that and you just go, oh, well, 5 minus 2, right? So I got 3. No, it's not. It's like add 5 to both sides. Like, don't mess up now. Especially in numeric response on the diploma, right? You get down to here and then 3, boom, wrong. Right? It's like, it did all that work correctly, and then just in the end, the last thing. The population of a certain animal can be represented by the formula P for population is 50 times 2 to the T over 5, where P is the population and T is the time in years since June of 1993. Complete the table of values. So when that's 0, what do we get? We get 0 over 5 is 0, 2 to the 0 is times 50 is 50. When T is 5, 5 over 5 is 1, 2 to the 1 is 2, times 50 is, when T is 10, 10 over 5 is 2, 2 squared is, times 50 is. So the initial population for June 1993, graphically this would represent the p-intercept, right? When t is 0, that's the p-intercept, and it's using the p and the t. So that's 50, right? According to the equation, the population will blank or increase by, so what's it doing every 5 years? So it's 50, 100, so it's doubling.
So 100%?
Or increasing by 100%, right? Just adding on the initial amount, which doubles it. So it doubles every 5 years. That's that t over 5, right? Like when the base is 2, then we're saying, well, every time we go up by a fact, every time the exponent increases by 1, we're going to double. And the t over 5 just sort of says, but it takes 5 years before you're going to go up by 1, right? So to get a 1 in here, it's 5. To get 2 in here, it's 10. Algebraically determine the year in which the population will reach 3,200. Assume none of the animals died during this time period due to natural causes or unforeseen circumstances, like a tree falling on it, which made the paper that you're writing this on. I didn't write that. I could have, but. So 3,200 is what we want, and we've got 50 times 2 to the t over 5. Okay, first step.
Divide by 50.
Divide both sides by 50, right? So what's that? It can't be 80. It's like 0. It's 5 into 320. 64? That seems reasonable. Because 64 be expressed as the power of 2, and it's 2 to the what? No. 2 to the 6th. whatever you think the number is, verify it somehow. You know, because if you throw a 5 in there because you think it's 5, guess what? It's wrong, and you know, no mark. So now what do we say? Well, we say 6 is equal to t over 5. So 5. So t is equal to what? 30. So it's 30 years, which is 6 doubling periods, right? Because it doubles every 5 years. So if you think about it, you've got 50, 100, 200, 400, 800, 1600, 3200. Right. I shouldn't have started with 50. The first doubling is 100, 200, 400, 800, 1600, 3200. Right? So 6. Exponential equations that cannot yet be solved by using a common base. So, if the base is not common, we can solve them graphically. Right? Use your graphing calculator. Once we learn about logs, we will have the skills necessary to solve them using an algebraic approach. But keep in mind, I mean, if you get this on a diploma, you can solve it graphically, right? It's going to be the value of x rounded to the nearest whatever. Just, you know, it's like, do the simple stuff. Okay? Like, you don't have to get complex. If you just say, hey, I can solve that graphically, solve it graphically. Now, if you go to graph it and it turns into a mess, like you really can't tell where the lines cross, like they're just too close together or something, and you can't zoom in, you're not really sure, because they really look like they're running along each other's lines based on the scale, then maybe solve it algebraically, right? Or kind of do both. So solve it graphically and then just put a little asterisk next to it. So when you're done and you got an hour left, you can come back and say, all right, now let me solve this algebraically, see if I get the same answer, right? Okay, so what do? Well, we can't express them as powers of the same base, right? So we're just going to graph them. So we're going to go y1 is equal to 1/2 to the x minus 1. So y1 is 1/2 to the x minus 1. y2 is 3 to the 2x minus 3. Calculator. Go to y equals. Going to clear what's in there, so if you've got anything in there, clear it out. During the diploma or any quiz or test, really, rather, if your calculator messes up, you get weird stuff, just reset it. Okay? So if weird things are happening, just reset your calculator. Okay, 1/2, so I'll show you the way. Bracket 1 divided by 2, bracket to the power of bracket x minus 1. So that'll work on an old school calculator, right? Like just any TI-83s or 84s without, just do it that way. Okay, and then 3 to the power of, and I'm just going to do the same deal here, 2x minus 3. Although it stays up there, you know, so here, but on yours you'll see a little upside down v. I'm going to go zoom standard. Let's just graph it in the standard window to begin with, and then we'll take a look. So we know that's the 1/2, right, because that's decay. It's going down. We're going to have another one that comes, it's going to go through here through 1. We're going to get the intersection somewhere around there, so it's there. Okay, so if we set a window, we say, well, let's go from, I don't know, 0, 1, 2. We can go from 0 to 2 by 0.5. So x, 0 to 2 by 0.5. Y values. Doesn't hurt to see the axis. So let's go like -1. Where are we here? We got 1, 2. -1 to 2. Come back. Okay. So window. What do we say? 0 to 2 by 0.5. -1 to 2 by 0.5. Make the point more obvious. Graph. Okay, there's a blue decay, right? That's the 1/2 going down. And there's the 3 to the power of. Okay, it's not quite centered, but it's okay, right? Then what? The important thing now is we find and we find the x coordinate of the point of intersection, right? So find the x coordinate or the x value of the point of intersection. Okay, second calc intersect. I just move basically to the point of intersection, or as close as I can get, and hit enter 3 times. So we got this 1.38 blah blah blah, and we say, can we change that to a fraction? So x math enter. Nope, we can't. Okay. So it said round answers to the nearest hundredth anyways. So 1.38. Okay, so x is equal to 1.38. So if I went and put the value, forget that. Why does it say it's got different? This is a different value of x than what I have. Everybody get the same value? Yeah. Oh, okay. So the key that's written here is apparently. Oh, I see. They went 2x minus 1 on the key. It's really a 2x minus 3. So if I put 1.38, went 1/2 to the 1.38 minus 1 and 3 to the power of 2 times 1.38 minus 3, are they going to come out exactly equal? Now let's try it. So 1/2, let's just go 0.5 to the power of, so 1.38 minus 1 is 0.38, right? Okay, and then I go 3 to the power of 2 times 1.38 minus 3. So am I going to get this exact value? No, why not? Because I rounded, right? Now, are they close? Is that close enough for you to say, yeah, it's 1.38? Okay, if you want to get the exact value, then do this. Whoops. So go to the power of x, right? Well, did x change? That shouldn't be. Oh no, it's 1 point. Oh, x minus 1. Hang on. To the x minus 1. Okay, that. And then do 3 to the power of 2x minus 3. Are they going to come out exactly the same? Yeah. Okay. So when you're using the unrounded value, you're going to get exactly the same. If you're rounding, they're going to be close. Okay. In this case, close was at least to the nearest thousand. Okay. First step. Do what first? Divide by 2. When we solve these logarithmically, you don't have to, but it makes it a lot more complicated if you don't. Right? But if you can, so you divide by 2. So you say 50 is equal to 7 to the x plus 2. So y1, and you go 7 to the x plus 2, and y2 is equal to 50. Okay, so we know the answer is around 2, right? Like 7 squared is 49, so the x is going to be like really small. Okay, it's going to be greater than 0, but come back. So y1, clear. 7 to the x plus 2, and y2, clear, 50. Zoom, standard, again, just do a standard window to begin with. Now you can see, okay, wow, there it is, and then here comes my, well, so wait, so 50. So obvious standard, that was dumb. Why would you do a standard window? We know that the answer is going to be a little bit over 0, right? So let's go from negative 1 to 1 by 0.5, and I need to see 50 in there, right? So, and really, we could just go pretty close to 50. So, say, I don't know, 48 to 52 by 1 graph. Okay, so there should be a blue line shooting up here in a second. And then coming right across the middle there. Okay, second. Calc intersect. Whoops. Not going to get that close. 1, 2, 3, 3. 0.01 to the nearest hundredth. Okay. So x window, negative 1 to 1 by 0.5. Y window, 48 to 52 by 1, and x is equal to 0.01. Okay, which makes sense, right? Because 7 squared is 49. You're not going to be much higher power than squared to get to 50. And the power is 1/100, 2.01. Why is x to the negative 4/3 not an exponential equation? Yeah, the variable, the base is the variable, right? So the variable is not the exponent. So the variable is not in the exponent. So exponential equation, the variable needs to be in the exponent. How do we solve x to the negative 4/3 is 81? So how do we get x, just x? How do we just get x? What can you raise negative 4/3 to get 1? Reciprocal, right? So negative 3/4. So the idea is we're going to raise, now whatever we do to one side, we have to do to the other side, right? So if I raise both sides to the power of negative 3/4, these multiplied together, you multiply reciprocals together, so that has to be negative, right? You need negative times a negative. So we get x is equal to 81 to the negative 3/4. So x is 1 over 81 to the 3/4, which is 1 over the 4th root of 81, all cubed. You could cube the 81, but it's really tough to find the 4th root of whatever 81 cubed is. But the 4th root of 81 is 3, and 3 cubed is 27. British calculator do that too, right? 81 to the negative 3/4. No, don't do it in the graph though. 81 to the negative 3/4. Math, enter. 1 over 27. Okay. But you got to show this, right? If this is determined, you're showing this work. You got to show this work. You got to show, I'm going from a negative exponent to a positive exponent. I'm changing it to radical form. So it's 4th root of 81 cubed, and then, wait, oops. Oops. Okay. Challenging exercise. Not challenging. Quadratics, right? So your first step in seeing this is, I got that 3 to the 2x, and then I've got a 3 to the x. So you just say, let's write this as 2 times 3 to the x squared minus 12 times 3 to the x minus 54 is equal to 0. Then we'll replace 3 to the x with, don't use x, right? Don't say let x equal 3 to the x. It's weird because you have x's on both sides. So you can't really do that. That would actually solve, like there's some value for which that's true. Maybe. So just let a equal 3 to the x. So I've got 2a squared minus 12a minus 54 is equal to 0. Okay, so we want to factor that. What, 9 and 6? Yeah, 18 and 6, that'll work. No, they're all even. Should have factored a 2 out, eh? Okay. So 2, well actually, so at this point you divide both sides by 2, and you just get a squared minus 6a minus 27 is 0. So a minus 9, a plus 3. So here's something that tells you you're doing this right, especially at this level, is if the a value, so a is some power of 3, right? So it's going to be 9 or it's going to be negative 3, right? So it's some power of 3. So now we say a is equal to 9 or a is equal to negative 3. So if it's 9, we end up with 3 to the x. Okay, so let a equal 3 to the x, right? So 3 to the x is equal to 9. So what's x? 2, right? We don't need to write 9 as 3 squared. Or 3 to the x is negative 3. So what's x? No values, no solution, right? No solution. You cannot raise a number to an exponent and get a negative value, right? Like you can get small values. Yeah, 3 to the x, I could make x a million and get 1 over it, but I can't get a negative 3 out of there. which is why this morning on Twitter, so Neil deGrasse Tyson asked John Allen Paulos, who's a relatively famous mathematician, I know you haven't heard of him, although you've probably heard of Neil deGrasse Tyson. So I've always wanted to divide by 0. Why can't I divide by 0? He's like, I know it's undefined, but what can you tell me? And he just said, well, you can divide by some infinitesimally small number close to 0, but smaller than any positive number. And that's the best I could do. Okay, you try this one. So I've divided everything by 2 first, right? Get rid of the 2 because they're all even. So do this. Let's go 6 to the x squared minus 37. 36 equals 0. Okay. Not much in the textbook of these particular type, right? So B and C are for you, just so you can see some. This is a little bit different. This is like I've got 2 equations and 2 unknowns, which implies a system of equations. So if we take equation 1, let's call that 2. So we could say 3 to the x minus y is equal to, so instead of 9, what are we going to write? 3 squared. So what does that now allow us to say? X minus y is equal to 2. So we have one equation, right? The other, number 2, we're going to write 3 cubed to the y is equal to 3 to the x plus 2. So we're going to change the 27 to 3 cubed. So now we've got 3 to the 3y is equal to x, is equal to 3 to the x plus 2. So we get to write what? 3y equals x plus 2. So you can solve by, yeah, substitution would work nice, eliminations, whatever. Okay, so here, solve that system. You got a system, solve it. Okay, the answer is down below. Okay, now, the answer is a point though, right? It's a coordinate, it's an x, y, it's a pair. Okay, it's not like there's not a value of x. There is a pair, there's a coordinate pair, x, y, because it's a point of intersection of 2 different graphs. Okay, and it's not just the x, y, we're not solving it. All the other equations were just had x in them, there was no y. Okay, and there's the solution. So we're done. You can do the other one, the rest of number 7. And